Hey everyone, today let's try to learn recursion and bitmasking. So first, what is recursion? Recursion is basically solving a subproblem in order to solve a bigger problem. Let's say we want to try first every node in a tree like this. It's pretty unclear how can we do it if we don't use some sort of recursion, because we don't have the access of every other node. For example, if I just take a look at here, I don't have access to this type of node, or the node that is not immediately the children of me. But if we use recursion, this becomes a very trivial problem. So what we need to do is that in order to visit all these things, then I'm going to visit my immediate children. And I'm also going to visit all the things from this point onward. So basically, I'm applying the same thing to me, to my children. So basically, if I want to visit everything from here, then I visit everything starting from here, and I visit everything starting from here respectively, and also separately. Then I will essentially visit everything in the tree. So that's the basic idea of a recursion. It is very useful in solving a lot of problems, and it's very essential idea in computer science. So let's take a look at what is bitmasking. So as confusing as it may sound, bitmasking is just using a binary number to represent a state or something. It can be anything. I will just give the example here. B stands for boy, and then G stands for girl. For example, we have a setting like this. You can imagine this is a row of chairs, and each chair represents that this chair is sitting on by a boy or sitting on by a girl. Instead of using like a string, we can use a binary number to represent it. Basically, if we use a BBG, then we can convert this thing into a binary number. 1 stands for boy, and then 0 stands for girl, for example. So you might ask, why is it necessary for us to do something like this? So first reason is that if we convert this string into a number like this, it is easy to pass in computer, and it's also easy to represent. For example, in this 1100, we don't have to keep a string. We can just use this 12 because it is the decimal representation of this binary number. We just have to pass this integer number, which is relatively cheap in a lot of the programming language. The second reason is that it's easy to do operations. For example, like XOR or 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 AND, they have some built-in support in those operations, and it is very, very fast to do this kind of operation instead of just writing code on it. Of course, you can do AND operation or XOR operation on this string, but it is not as efficient as doing the binary operator here, because they are heavily optimized by the programming language. So let's take a look at what we can do with those binary operator. Let's go back to our first example. This is like a sit for a row, and then this is, you can imagine, is like a classroom. This is the first row of sit, and then the second row of sit, and the third row of sit. So now if we represent this as binary numbers, we can do some interesting operations. For example, if we AND all the numbers, we will get something like this: 1 0 0 0 0. So what does it tell us? Well, it tells us that this number is 1. It means this position, this particular position, or any other position that has a 1 after the AND operator, means that every student in this particular column is 1. And if you take a look at any other column, and you will see that there's some girl in the middle, or some girl at the beginning, or some girl at the last. So it is one interesting application after converting this whole thing into a binary number. And let's see one more problem that we can use recursion and then bit masking to actually solve it efficiently in LeetCode. In this problem, basically you are given a tree. Inside a tree, each edge will have a label like A, or a label like C, or a label like C, or a label like B, or a label like A here. So we have a tree, and each edge will have a label, which is a lowercase character. And what we are trying to return is the number of pair of nodes such that the path between them can be rearranged into a palindrome string. So let's take a look at the first example here. So this is returning 8. Why? So if you look at this from 0 to 1, and there's like this C. So C is just a possible palindrome, and also this A is also a possible palindrome. Actually, there are like 5 and 1, 2, 3, 4, 5 of edge. These 5 edge by themselves are going to be palindrome. So we're just going to do 5 here, and then let's check other pairs like this one from 3 to 5. Let's see the path from 3 to 5. So you have to go to here, and then you have to go to here, and you have to go to here, and you have to go to here. And by the way, because we know that this is a tree, so there's a property of a tree. Every node will have exactly one path between them. For example, if there is another path like this won't be a tree. In fact, if you think about it, if there is 2 or more paths from here to here, then there is a cycle, because you can go for the first route because we know there is a first path, and then you can come back from the second path. So that means there is a cycle. But the problem statement given that there's no cycle. That's why we can be reassured that each node pair will only have one path. So we only care about this AC, AC. So let me write from node 3 to 5 is going to be AC, AC. So wait a second, you might say, it is not a palindrome, but the problem is trying to ask us not for the exact palindrome, but more like the potential to be a palindrome. So of course this A, or B, A. Of course, if the path is like this, then of course you're going to count it as the answer. But this is also part of our answer, because if you rearrange this A, C, C, A, if you rearrange the characters like this is actually a palindrome. So the palindrome requirement for this property is actually more linear than strictly asking a palindrome. That's why if the path looks something like ACAC, this still count as a palindrome. So now we have 5 and plus 1 for this thing, and we're gonna check another node. Let me use a different color. This thing is from 3 to 2. Let's see, from 3 to 2. So what is the 3, 2? The 3, 2 is ACA. So by itself it's already a palindrome, that's why we added. And let's check another pair. Let's say from 4 to 0. So from 4 to 0, we get a path from BC. So BC is not a palindrome. No matter how we rearrange it, it's not going to be a palindrome. That's why we don't add 1 for it. So these 2 can be added, and this cannot be added. And let's go one more example from 1 to 5 this time. So 1 and 5. From 1 to 5, you can see the first one is C, A, C. CAC by itself is palindrome, and then you can plus 1 again, and the total answer is 8, which is what we see here. Actually, I have covered all the node pairs, that's why we are returning this 8. So that's basically all of the problem description. Now let's see how can we link the bit masking and recursion into solving this problem. Take a look at the input. If they give something like this. The first step is to convert them into a graph, and it will look something like this. We also have the S, which basically means the character of each path. So this 0, 1 should have a C. Oh, this is A, this is A, this is B, this is C. So now we already have this graph. How do you come up with the idea of using bit masking? So if you look at this and think about what a palindrome is. So a palindrome means a string that reads the same from start to end or from end to start. That's the definition of a palindrome. I can give you some examples. So ABA is a palindrome. AABB AA is a palindrome. BBCC BB is also a palindrome. Now we can try first the tree using some sort of DFS. For example, this path will be CA, and then what should we record? Should we record the frequency of C and we also record the frequency of A? Do we actually need to record the frequency of those? Let's take a look at these palindromes. In here, A appeared twice and B appeared once. And in here, 8 appears 4 times, and then B appeared twice. And in here, B appeared 4 times and C appeared twice. So what you would notice is that except for the middle one, all other characters from the beginning or from the end, they must have an even frequency. Why? Because if they don't have a frequency of an even, so something like this will match with this, and then this A will have nothing to match with. That's why every character frequency should be even except for only one character. So we have one option that could be odd, which is why we can put them in the middle. So this CCC, even though it is odd, but if we just take this, then we'll just place the things in the middle, and this thing also works. So that's the main idea. We don't have to record every count of the character. Instead, we only care even or odd so far. So at the beginning, everything is even because we don't have any frequency. So we will have a binary string of 26. 0 stands for even, and 1 stands for odd. That's how we're gonna define this. So at the beginning, everything will be 0. I'm not gonna write 26 lines, but you can imagine there will be 26 0. And if we do some recursion and go down here, and C is here, the number 3 of the binary number, so it will be 0 0 1 0 0 0. Again, the size of this binary number will be 26, so there's a lot of 0. We go to here, and then A will be something like 0 1 0 1 0 0 0. And then if we choose to not go to A, we go to B instead. It will have 0 1 1 0 0 0. And here, if we go to A, it will be 1 0 0 0 0. And when we go to C after visiting here, we will have 1 0 1 0 0 0. So that's basically the idea. First, we're gonna have this binary bit for each node. And actually, this already half of the solution is done. What is remaining is that how can we use these numbers or this frequency? So for each binary number, if they are exactly the same, something like this, if they are exactly the same, it means that there is a path in here to here, and another path is here to here. This is the path, and this is also a path. What we can do is to combine these two paths. Then we will have a palindrome arrangement string. Let's see what happens when we try to combine it. So if we combine this, it will be AC here, and then another AC here. So AC. So we can rearrange them to A, C, C, A, or C, A, A, C. So it doesn't matter. It just means that it is possible to form a palindrome arrangement from here. So what we want to do is to just try first every bit, and then answer plus equals to frequent of this bit times frequent of this bit minus 1. Why minus 1? Because we can't match it with itself. So that's why we have to minus 1. So if we just do frequent bit square, then it means that it will match itself. So for every node, it will only pair everything of the same bit except for itself. So at this point, you might be asking, what about the pair? So in this case, we will count AB and also BA. So to kind of repeat it. So by the end of the whole operation, then I will do a divided by 2 operation to handle this issue. So what about something like A and then C and then A? So instead, look at this one. It is possible to match 3 and 2, but they are having a different binary number. What should we do? It is acceptable to have 1 or less bit that are on after the merge, let's say. So in here, let's say 1 0 1 0 0 0, and this one is 1 0 0 0 0 0. If we merge these 2 paths, basically is this path and this path. So if we merge these 2 paths, we will have the remaining of this one. So basically in programming, we can do an XOR, but all the other things will be 0. We only have 1 that is remaining. We just put them in the middle. So it is acceptable. For instance, this AA, we can match here, and for the OR, we can just place it on the middle. So it just kind of works as well. But how should we do this programmatically? Apart from doing this thing, we can also do another operation to accept when there's only one difference. For example, we can iterate the position for bit position from 1 to 26. So basically, in this number, first we're going to check if it is on. If bit post is 1, so if it is 1, then we want to know that 0 0 1 0 0 0. We want to know this thing. So if it is off, then we want to know 1 1 1 0 0 0. Because if we change this particular bit, invert them, and after the inversion, then I apply XOR to the new bit, and the remaining result will have a bit count of 1. And that is acceptable, but we didn't capture that in here. So there's a quicker way to do this, is that we're just going to bit, is the current bit that we are interested in, and XOR 1 to the bit post. Basically, we will just shift 1 to the bit position, and then we try to apply the XOR to obtain a new bit. Once we have the new bit, and this is the new bit that is acceptable, if we XOR this new bit for bit, we will have exactly 1 difference, because the only 1 difference comes from here that I made. So for each frequent bit, and they can match with frequent new bit. This time I don't have to minus 1 because, well, new bits, it's a different bit than here, so I won't recalculate it or matching itself by doing this. That's why eventually I will just have to do all this thing and answer plus equal this, and then eventually just return the answer and divide it by 2, because from now we still have the A, B, and then also counting BA issue. So that's pretty much all for the intuition, and let's see how can we code this up. So in the beginning, I'm just going to convert this parent into an adjacency list because it's more convenient to do operation in an adjacency list than a parent, because I can sort of loop through every child in an adjacency list but not in a parent list. After converting them into an adjacency list, the next thing we can initialize a frequency of bit, which just basically mean how many times this bit has appeared. And we're gonna define a DFS function. So I is the current node that we're visiting. From is what is the index that it come from. We record this because we don't want to revisit the parent. Because if we visit the parent again, and the parent visit the child again, we will have some sort of loop. And then bit is the 26 sized binary number that we mentioned before. 1 is stand for odd, and then 0 is stand for even. And we have 26 size of them because there are 26 lowercase characters from A to Z. And we're just going to add the bit count by 1 because we just keep the record, keep the frequency, add it by 1. And then for each neighbor, for this current bit, if it is coming from the parent, then we're just not gonna revisit it. And then we're just going to visit it otherwise and just set this coming from I, because current is I. And then bit is this thing. The current bit XOR the character is the character position. A will be 0, and B will be 1, and C will be 2, etc., etc. So after applying this XOR, it's just basically saying something like, if it is current is odd, and if we add this current character, we will go from odd to even. And if it currently is even, and after considering this character, it will go from even to odd. That's basically what this means. Then we're going to initialize our DFS as 0, -1, and 0. So we start from 0, and then -1 is because we're coming from nothing. We just initialize that at -1. And bit currently is 0 because nothing is set yet. All the frequency of the 26 lowercase characters are 0. So that's why we just put a 0 here. And after doing all this calculation, we're going to use the frequency of bit somehow. So now we're going to use it on line 17. First, we're going to initialize the answer as 0, and you're going to iterate every bit inside the bit that we have seen. And this thing, this line 19, is to consider the bit that are exactly the same. And then line 20 is to iterate every position of the bit, of the current bit, and try to negate one of the position. So if this new bit XOR this bit will have exactly one difference, because that exactly one difference is coming from this one go to position XOR bit. And then we have to consider that it is possible that this doesn't exist. So if it doesn't exist, we're just going to make it as 0. And then eventually we can just return answer divided by 2. As I mentioned before, if we don't divide it by 2, we are basically calculating A, B, and also B, A. So we only want to consider one of them if they are the same pair. We don't want to compare twice. So that's why we have to divide it by 2 and return it as the final answer. Okay, let's try to submit that. Okay, accepted. It is a pretty hard problem, and I hope I have explained it well, and I will see you next time. Bye bye.